Hello everyone, my name is Bogdan Dushan and I will present here the results of our study on the evaluation of manual and semi-automatic laughter annotation. Laughter is a pervasive phenomenon in spontaneous interactions, and its importance in communication is mirrored by the interest it sees in the scientific community. Despite its interest, laughter and annotated datasets are not that common, and multilingual corpora annotated for laughter and containing comparable materials even less so. We look here into possible solutions for this issue by exploring the process of enriching existing corpora with laughter annotations. How can one achieve this? We can always annotate laughter manually, but as with any other manual annotation process, it will be time-consuming. Moreover, there is no information available in the literature on how long this might take. Another option would be to do everything automatically, but the output of laughter detection systems is not good enough for more fine-grained analysis. A third option would be a semi-automatic approach, which combines the advantages of the previous two methods, namely, it provides high-quality annotations in less time. The goal of the current study is twofold. First, we examine the process of manual laughter annotation in speech corpora, independent of other types of annotations. For this, we determine two important parameters of the task: the required annotation time and the reliability of the process. Second, we investigate ways to facilitate this process by proposing a novel semi-automatic annotation procedure. It employs a signal-based method to automatically determine the regions that might contain laughter, regions which are then used to constrain a manual laughter annotation step. The proposed method is based on a speech rhythm representation shown to be able to discriminate laughs and speech laughs, which are two types of laughter from speech. We employ here the dual corpus, which contains spontaneous interactions and has been manually annotated for laughter. More exactly, we make use of data from two scenarios: film script and dream apartment from the German part of the corpus. 8 recordings from the first scenario were used for the building of the tool and for setting its parameters, while 4 dialogues from the second scenario were employed for testing the tool and for the annotation experiment. The automatic laughter pre-annotation tool uses the AM/FM spectra toolbox to compute a speech rhythm representation called the modulation index by means of a large analysis frame, 1.5 seconds long, and using an overlap of 15 milliseconds between consecutive analysis frames. The modulation index characterizes the amount of change in the different frequency bands of the speech signal as a function of the change rate. To compute it, the input signal is first bandpass filtered with a gammaton filter bank with 30 channels, and the envelope of the output of each filter channel is extracted. After filtering them with a bank of Butterworth bandpass filters, DC normalization is applied, in which the root mean square amplitude of each filter output is divided by the mean amplitude of the output of the gammaton filter. Finally, we stack the output of all the 30 channels in order to form a 3D representation similar to a spectrogram. It contains the modulation rate on the OX axis, the spectral frequency on the OY axis, and the modulation index amplitude as the color of each point. In the first step, we compute the modulation index of all the instances of laughs, and speech from our film script scenario recordings, and we determine the average representation of each of the free vocalization classes over the entire data. Next, we calculate the average between the representations of the two laughter classes, so laughs and speech laughs, and subtract from it the representation of the speech class. The resulting difference matrix should exhibit higher amplitudes in the frequency ranges, more salient for laughter and less so for speech. Then, at runtime, we compute a detector function based on the modulation index of the input file. For each analysis frame, we take only the points of the modulation index representation which surpass a certain threshold. The value of the detector function for that particular frame will be the average of the points of the modulation index that exceed that threshold. Once the detector function for the entire recording is computed, it is smoothed using a sliding window, and then laughter event candidates are considered by searching for the local maxima of this function. The candidates must have a peak prominence of at least min prom compared to the neighboring minima. And finally, the tool will return 5-second long intervals centered at the time of each laughter event candidate. We evaluated the performance of the automatic tool with respect to the manual laughter annotations supplied with the corpus and using classic measures, precision, recall, and F-score. The three parameters employed by the tool were determined on a development set composed of one recording from the film script scenario in order to maximize the detection F-score while keeping the precision higher than 0.8. So we have here in this table the results obtained on the development set and the test set. The test set consisting of 4 recordings from the Junior Parliament scenario. We can see that a slightly lower performance was obtained on the test set than on the test set, one that favors recall rather than precision. For the annotation experiment, we used 15 minutes from the test set, so a recording of 15 minutes from the test set, for which the tool had the most similar performance to the overall set. 7 annotators, having experience with phonetic annotations, took part in our experiment. They performed both the manual and the semi-automatic task in consecutive weeks, 5 to 6 days apart. 4 of them did first the semi-automatic task. They received a prod text grid containing the regions of interest on one tier and were requested to annotate the laughter events, both laughs and speech laughs, found in these regions on a different tier. The regions of interest for the manual task were the parts of the dialogue that contained speech, while for the semi-automatic process, the automatically determined laughter intervals. 3 measures of interest were computed: the time required to perform the annotation task, the inter-rater reliability in the form of standard metrics such as inter-rater agreement and kappa measure, and lastly, the number of laughter events annotated. With regard to the annotation time, our participants took on average 75 minutes to perform the manual task, while the semi-automatic process was shorter, around 52 minutes. This difference was found statistically significant when tested with a Wilcoxon signed rank test. For the inter-rater reliability measures, we analyzed 2 cases. When we consider laughs and speech laughs as 2 separate classes, and when we view them as belonging to a single class, laughter. As expected, the reliability in the former case was lower than in the latter case due to a higher ambiguity. Nevertheless, in both cases, substantial agreement was observed between annotators. Also, no significant difference was seen between the manual and the semi-automatic process. The last measure we looked at, the number of annotated laughter events, revealed an average of 87 instances in the manual case, of which 62 were laughs. The semi-automatic process produced on average 10% less events than the manual one, 78 instances with 56 of them being laughs. Difference found to be statistically significant. An observation here is that the events that were missed in the semi-automatic task had low kappa values in the manual task, and all of them were very short events. I had here an example of such a non-typical laughter that was not detected by the automatic tool. I'll play that again. So you can compare it to a more typical laughter that was found by the proposed system. So we investigated here the process of laughter annotation independent of other types of annotations, and our results on estimating its required time represent a first such attempt. We believe that our estimate is quite robust as it is based on data from 7 participants. Nevertheless, one must take into account when designing an annotation campaign that the required annotation time may be modulated by several factors pertaining to speaking style, such as the proportion of speech in the recording or the amount of laughter in the conversation. Regarding iterated reliability, we observed that by using 7 non-expert annotators, we obtained similar results to those of a previous study that used 2 expert annotators. The result is encouraging as it suggests that the reliability might not vary with the number of annotators nor with their expertise. To summarize, we determined in our study 2 important parameters for the laughter annotation process: the time required, about 5 times the duration of the recording, and its inter-rater reliability, ranging around 0.7, 0.8, which indicates substantial agreement. Moreover, we propose a semi-automatic approach which reduced the annotation time by about a third for the same reliability and at the cost of 10% missed laughter events. Since all the missed events represent non-typical laughter instances, we intend to focus our future efforts on features allowing the discrimination of these types of laughter from speech. Thank you for your attention.